Before we start factor analysis, let's review the classification of multivariate techniques. Classification is based on whether the variables can be divided into dependent and independent classification. The dependence techniques are on the left side and interdependence techniques are on the right. A dependence technique may be defined as one in which a variable identifies the dependent variable to be predicted. An example of a dependence technique is multiple regression analysis. In contrast, an interdependence technique is one in which no single variable is defined as being dependent. Rather, the procedure involves the simultaneous analysis of all variables in the set. Factor analysis and PCA are examples of an interdependence technique. As with dependence techniques, the measurements property should be considered. And generally, factor analysis and cluster analysis are considered to be metric interdependence techniques. However, non-metric data may be transformed through dummy variable coding. And if the interdependencies measured by non-metric data, correspondent analysis is also an appropriate technique. Let's review the concept of dimensions. When we have a simple data matrix M where each row represents an observation in the space, also called sample, and each column represents an attribute, also called dimension, we say you have, for example, 150 observations and 4 dimensions. Not all attributes or dimensions will contribute well to our model. Some irrelevant and correlated attributes can even decrease the performance of some algorithm, contributing to overfitting. Factor analysis and PCA play a role in the reduction of these dimensions while preserving the essence of data. Factor analysis and PCA are very similar, and both are statistical approaches to analyze interrelationships among a large number of variables. And they explain these variables in terms of their common underlying dimensions or factors. They follow the same steps: extraction, interpretation, rotation, and choosing the number of factors or components. Factor analysis, however, makes assumptions, while PCA does not. And the basic assumptions that there are implicit features responsible for the features of dataset. And in principal components, we define new variables, factors, which are linear combination of observed variables that summarizes our input data. And the focus is on expressing new variables, principal components as weighted averages of the observed variables. In common factor analysis, we infer the existence of latent variables that explain the pattern of correlations, and thus we focus on expressing the observed variables as a linear combination of underlying factors. The following analysis may clarify a bit a concept for factor analysis. So what underlying attitude lead people to respond to the questions on a political survey? So we can examine correlation among the survey items that will reveal that there is significant overlap among various subgroups of items. For instance, questions about taxes tend to correlate with each other, or questions about military issues may correlate with each other. With factor analysis, we can investigate the number of underlying factors. And additionally, we can compute factor scores for each respondent, which can be used, for instance, building regression model. When we deal with univariate techniques, they are limited to a single variable. But multivariate techniques can have tens or even thousands of variables. And as we add more and more variables, more of them will overlap. How to manage these variables? Factor analysis is a multivariate technique that examines the interrelationship among a large number of variables, and it attempts to explain them in terms of their common underlying dimensions. And these common underlying dimensions are referred to as factors. Factor analysis is summarization and data reduction technique that does not have independent and dependent variables, but it is an interdependence technique in which all variables are considered simultaneously. Some of the useful terminology that we can review. Variance is how far the data is spread out. Unique variance is the variance of the variable that is not associated with other variables. Shared variance. The variance can be shared with one or more other variables, creating redundancy in the data. And redundancy implies that you can find the same information with slightly different values in various features and across many observations. And variate is a linear composite of variables. An illustrative example of a simple application of factor analysis is shown in the figure on the left, which represents the correlation matrix for 9 store image elements. Measures of product offerings, store personnel, price levels, and in-store service and experiences. The question we would like to ask, are all of these elements separate in their evaluative properties, or do they group into somewhat general areas of evaluation? Visual inspection of correlated matrix shows that we do have some high correlated variables, but we do not see any specific pattern. The application of factor analysis results is shown in the figure on the right. First, we see that 4 variables relating to the in-store experience of shoppers are grouped together. Then we have 3 other variables describing the product assortment and availability, and they're grouped together. And finally, product quality and price levels are grouped. Each group represents a set of highly interrelated variables that may reflect a more general evaluative dimension. In this case, we might label this 3 variables grouping by the labels in-store experience, product offering, and value. The simple example of factor analysis demonstrates the basic goal of grouping highly intercorrelated variables into distinct sets of factors. Factor analysis is widely utilized in market research, advertising, psychology, finances, and operation research. For instance, market researchers may use factor analysis to identify price-sensitive customers or identify brand features that influence customer choice. Factor analysis provides us with 2 distinct but interrelated outcomes: data summarization and data reduction. Data summarization derives underlying dimensions that, when interpreted and understood, describe data in a much smaller number of concepts than the original individual variables. Data reduction extends the process of data summarization by deriving an empirical value, in this case factor score, for each dimension, and then substituting this value for the original values. The goal of data summarization is achieved by defining a small number of factors that represent the original set of variables. The goal of data reduction is to retain the nature and character of the original variables, reducing their number to simplify multivariate analysis. There are 2 types of factor analysis: exploratory factor analysis, which is used to discover the factor structure of a construct and examine its reliability, and it is data-driven. Confirmatory factor analysis is used to confirm the fit of the hypothesized factor structure. It is theory-driven. Factor analysis models the variability by projection from a high-dimensional space to low-dimensional space, for example, from 3D to 2D. Each observable variable is a linear function of independent factors and error terms. The parameters beta are referred to as loadings. For example, beta 1 is called the loading of variable yi on factor f1. From linear function, we can calculate the variance for the variable y. We see that the variance of yi consists of 2 parts. The first, the commonality of the variable, is the part that is explained by the common factors, f1 and f2. The second, the specific variance, is the part of variance of yi that is not accounted by the common factors. Loadings are the weights that the variable has for constructing a factor, and the higher the load is, the more relevant in defining the factor's dimensionality. The factor loading is a matrix which shows the relationship of each variable to the underlying factor. We can describe factor analysis as a 2-step process. In the first step, factor extraction, the number of factors, and approach for extraction selected using variance partitioning methods. The eigenvalue is a good criterion for determining the number of factors, and generally an eigenvalue greater than 1 will be considered as selection criteria for the feature. Or we can use scree-plot to determine the number of factors where the curve makes an elbow. In step 2, factor rotation. Rotation tries to convert factors into uncorrelated factors. This refers to a rotation of the axis in a coordinate system. And there are a lot of rotation methods that are available, such as Variance method, for instance, and orthogonal rotation method that minimizes the number of variables that have high loadings on each factor. And this method is very commonly used. Notice the scatter plot of the unrotated model on the left. It has points in the middle of upper right quadrant. There are not many high or low loadings, and most of them seems to be very moderate in size. Now look at scatter plot on the right, using a Variance rotation. Notice how points are now clumping around axes, and they're high on one axis but not on the other one. So the Variance method simplifies the interpretation of the factors. Now it's time to perform factor analysis. Let's import the data and check the basic descriptive statistics. We notice that variable ID is a unique number, and we can remove it. We can drop it from the dataset. Our next step is inter-item correlation analysis with core plot. We can see highly correlated variables. For instance, compress and del speed are highly correlated. Let's compute now p-value for correlation pairs and plot only significant pairs. Our core will compute a matrix of Pearson correlation coefficient for all possible pairs of columns of matrix. Missing values are deleted in pairs. However, if we were to run a multiple linear regression on this data, we would violate the assumption for not having any multicollinearity. Remember several assumptions that we reviewed last week for linear regression, such as linearity, homoscedasticity, residual normality, and no multicollinearity. Let's check for multicollinearity factor via F, high variable inflation factor. We notice we have several variables greater than 2.5, which may cause concern. In step 3, we'll be creating a new data set by taking subset only of independent variables. We'll remove satisfaction variable and then perform a Kaiser-Meyer-Olking test. KMO test measures the suitability of data for factor analysis. KMO values range between 0 and 1. Value of KMO less than 0.5 will be considered inadequate. The results show that the test value is 0.65 and factor analysis is appropriate. Step 4. Determining number of factors. One way to determine number of factors or components is to examine the scree plot of eigenvalues. Based on the scree plot, let's use 4 factors to perform a factor analysis. And also let's use orthogonal rotation Varimax, because in orthogonal rotation, the rotated factors will remain uncorrelated. In step 5, we run factor analysis. The output gives us a summary for loading weights of variable and cumulative proportion of factors. In this case, we have 69% of data variance explained, if you look at the cumulative variance. Factor analysis results are typically interpreted in terms of major loadings on each factor. And these structures can be represented as a table of loadings or graphically, where all loadings with the absolute values are represented as an edge. We can effectively reduce dimensionality from 11 to 4 while only losing about 31% of the variance. To run regression analysis with factor analysis output, we need to first extract scores from factor analysis. Then we need to combine response and predictors and label our factors. If you look at the table on the right, top right is example of scores. We need to look at our variables to decide what label to assign for each factor. In the case of factor 1, our variables are speed, compress, water billing, so we can label it as a purchase. In the factor 2, for instance, we have sales image, e-com advertising, so we can label it as a marketing, and so on. Now we need to split data in the train and test dataset and train model. The summary of the model presented on the right, but we need to still check for multicollinearity by running VIF function. And you notice all factors are less than 2.5. Our regression model show that the factor purchase, marketing, and prod positioning are highly significant, but post-purchase is not significant in the model. And finally, we can run prediction on the test data, and then we compare the actual data with prediction data.